Hi everyone, I'm back. Lesson 8, the last lesson of this unit. I will be making a review lesson for you, so be ready for that. So Dalton's law of partial pressure. Our objectives, actually we only have one. In this lesson you're going to state and apply Dalton's law of partial pressure to problems that are involving a mixture of gases. So the law of partial pressure. In a mixture of gases, the total pressure of the mixture is the sum of the partial pressures of each component gas. So here is an example to apply this equation here, okay, and this is something that you'll have to memorize. The total pressure of 3 gas components in a mixture is 550 torr. If the pressure of gas A is 200 torr and the pressure of gas B is 75 torr, what is the partial pressure of gas C? Because it says 3. So we have gas B is 75. Okay, remember the total, okay, P total is 550 torr, and that's going to equal A plus B plus C. All right, so 550 equals 200 plus 75 plus C, and therefore C is equal to 275 torr. Okay, easy enough? All right, so they're going to get a little more difficult as we go. So the first example here, let's do some to apply this. A mixture of oxygen, nitrogen, and hydrogen gases exerts a total pressure of 74 kilopascals. The partial pressure of the oxygen is 20, and the partial pressure of nitrogen is 40 kilopascals. What is the partial pressure of the hydrogen? So this is going to be your P total. They give this to us. Our P total is equal to 74.0 kilopascals. Okay, the partial pressure of the first gas, or the oxygen, is 20. Make sure all of your units are the same. Pressure 2 of the partial pressure, how do I want to say it? Okay, partial pressure of nitrogen, sorry guys, 40, brain fart, kilopascals. Now we need to know the pressure or the partial pressure of the hydrogen in this mixture, so we'll say that's gas 3. So when we set this up, we're going to say 74.0 is equal to 20 plus 40 plus whatever the hydrogen is, okay, or the partial pressure of 3, should I say. All right, so 74.0 equals 60.0 plus our partial pressure of the hydrogen. Therefore, the hydrogen's partial pressure, and I'm going to just put H2 because this is hydrogen gas, is going to be 14.0 kilopascals. All right. Next problem. 2. A cylinder is filled with 2 moles of nitrogen, 3 moles of argon, and 5 moles of helium. If the gas mixture is at STP, what is the partial pressure of the argon? So we kind of have to figure out a fraction here, guys, okay? If the total is got to be the sum of all, right? So if you have 2 moles of nitrogen, 3 moles of argon, and 5 moles of helium, we add up the number of moles and we get a total of 10 moles, right? So that's 2 plus 3 plus 5, okay? Now we need to figure out what fraction of this entire thing, or a partial pressure, partial moles of this entire thing, to figure out what the partial pressure of argon is going to be. Basically, since it says it's at STP, the total pressure, P total, has to equal 1 atmosphere, okay, because that's STP. That's where we get the P total from. Now, if we figure out the fraction of that entire thing, according to this, we know that we're looking for argon, so this is 3 moles of argon. Okay, and this is a little tricky now. 3, we're getting the partial molar, I guess I should say, out of this. So 3, the moles out of the whole is 3/10. So that is actually equal to 0.3 as far as the proportion goes. All right, so if we want to know what pressure that contributes, okay, we're going to say that 0.3 moles is going to contribute to the total. So we're going to just multiply 0.100 ATMs times 1/3 of what the total would be, okay, because that's what it takes up, and we're going to get 0.3 ATMs. Now these are the trickiest because we're talking about moles, and really what you need to do is just simply figure out the part out of the whole. okay, and then apply it to the total pressure. Little ratios again to help us figure this out because we're dealing with moles. So we have a total of 8 moles for our total, okay, and that makes up 4 moles of oxygen and 3 moles of hydrogen and 1 mole of nitrogen. So we're basically figuring out the part divided by the whole here to give us a fraction or a percentage of the entire pressure. Again, it tells us that we are at standard pressure, okay? So standard pressure is equal to 1 atmosphere. So we need to apply our ratios here. So we're talking about just the hydrogen gas. So if we look at this right here, okay, it's 3 out of an entire 8 moles. All right, so you have 3 out of 8 moles. That's going to give us our fraction, okay, or our percentage of the pressure, basically, or what it makes up out of the entire mixture. Okay, so that's 0.375. So now we're just going to apply this to the entire thing. We're going to multiply this by the total pressure. All right, so P total is going to equal 1 atmosphere. Okay, and then if we actually do this out here, we have 0.375 is going to be your hydrogen, because we need to multiply this by 0.375 like we did in the previous example to give us the partial pressure of the hydrogen. And if we want to double check ourselves, we can go in and figure out for everything else. So the pressure of the oxygen, let's say, okay, is going to be 4 out of 8, right? 4 moles out of 8, that's our ratio, is 0.5, okay, times our 1 atmosphere is giving us 0.50, okay, as our partial pressure for oxygen. And then let's try nitrogen. So partial of nitrogen, and going back up, is 1 out of 8. 1 out of 8, okay? Gives us 0.125. And we multiply that by our 1 atmosphere. Again, we get 0.125 is the partial pressure of the nitrogen. Remember, this was the main question, okay? But we just want to double check and make sure this all adds up to 1 atmosphere, because the partials have to add up to the total. So if you plug that in, we say 0.375 plus 0.125 plus 0.5, and our P total does check, okay? And this is how we check our work. 1 atmosphere. Yay, it is checked. Check, check, check. Okay. So to end this lesson, our last page in our notes, for some reason, goes back to density, but we do want to relate this to gases as well. So density is the quantity of matter in a given unit of volume. Remember, density equals mass divided by volume. So if we're taking a look at these 2 boxes, each box has the same volume because they have the same size or same shape, I guess, and same size. If each ball has the same mass, which box would weigh more and why? Okay, here's your answer. The box on the left would weigh more because it has more balls in the same amount of space. Okay, it's the same volume, and each ball has the same mass, but if you look at the picture, we have more in here than over here. So we have to say that this one is going to have more mass. Okay, and so for the last part, again, the box has more balls, has more mass per unit of volume. This property of matter is called density. So the density of a material helps to distinguish it from other materials. So it's given, we know, since mass is usually expressed in grams and volume in cubic centimeters, it is generally expressed in grams per cubic centimeter. 1 cubic centimeter is also equal to 1 milliliter. So that's why we can say grams per milliliter for volume as well. Because of this, okay? So if you ever hear, if you go to the hospital and the nurses say, oh, we need, 5 cc's, okay? Cc's are equivalent to 1 milliliter or cubic centimeters. That's what that stands for, cc, cubic centimeter, okay? So in medical terminology, 1 cc is equal to 1 cubic centimeter, which is also equal to 1 milliliter. So that's how they make their measurements in volumes. All right. So lastly, I want you to do numbers 1 through 6 on page 20 of your practice packets. I will check it in class. And also I want you to jot down any questions you have about any of the video lessons. You will have a test on Unit 6 next week.